We'll all learn Taylor series. So first, let's define what a Taylor series is. It's going to be a power series. Simply defining the Taylor series as a power series that can be thought of as a Taylor polynomial that goes on forever. And then the Taylor polynomial centered at x equals 0 for cosine of x would be seen as this. Would equal 1. Okay, so whenever we're doing a Taylor polynomial of cosine of x centered at x equals 0, you would take the first derivative of cosine of x, giving you negative sine of x, and then whenever you plug in 0 for all of those, you're gonna end up getting like 1, and then if you do like the second one, like the second derivative, you would end up getting like negative 1, and so just go back and forth, leaving out the odd numbers because of the way that you take the derivative. And then so for your final, if you were to do cosine for your final, if you do cosine of x, the 8, you end up getting 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So that would be your 8th term for the cosine of x. Up on the board, this is just the first 3 of some Taylor series that you should just know pretty much off the top of your head. They're pretty easy to memorize. Like you can check them by plugging in the zeros or taking the derivative. But this is the general term for them. And then if you plug in this, they'll all prove for that, and they all have an interval of convergence and a rate of convergence of infinity. Here are just 3 more of some Taylor series that you'll need to memorize. And the only difference with these is their interval. This is a closed-off interval because it's just the way they calculate it out. And then for these ones, they are open intervals on -1 to 1, and the rate of convergence is also 1. Alright, and these are the last 2 Taylor polynomials that you should just kind of know as general memorization.
All right, this is Joelle in Essex, and I just wondered, did you find something?
Okay, so this is going to be how to find the parent function f of x about the point x equals 0. A function whose derivative exists as 0 is a Taylor series. Taylor series of f does not necessarily converge to f of x for all values of x. For the values of x for which the series does converge to f of x, we have is your parent function.
This is fine.
So this is your parent function. You find it by taking f of 0 as your first term, and then the derivative, and taking f of the derivative of 0 and multiplying it by x. And then you keep going like that and dividing by the factorial of the number of degree that you're on. And this is your general term, but that's only when it's centered around 0. If it is centered around another point A, we would then say f of x equals f of a plus f of a times x minus a plus f of a times x minus a squared over 2 factorial plus f triple prime a times x minus a to the third over 3 factorial plus, and your general term is about the same, f of n times a x minus a to n over n factorial. So the only real difference is that you're going to be subtracting your a value from your x when you have a different point other than 0. Okay, so our first theorem is the form of a convergent power series, and that's going to be if f is represented by a power series, f of x equals the summation of c sub n times x minus a raised to the n for all x in an open interval L containing a. So your c sub n is going to equal f raised to the n of a over n factorial. And your f of x is going to equal f of a plus f prime of a times x minus a plus f double prime of a x minus a over 2 factorial plus and your general term is going to be f of n x minus a to the n over n factorial. So if a power series converges to f of x, then the series must be a Taylor series. Right. So for the definition of a Taylor and Maclaurin series, if a function f has derivatives of all orders x equals a, then the series will of all orders x equals a, then the series, which is just your regular parent function, is called the Taylor series for f of x at a. If a equals 0, then the series is called a Maclaurin series of f. Yep. So the first example, we're going to do e to the x centered at 2. And now, e to the x is just one of your ones that you need to have memorized. And we're only doing it to the 3rd degree. So 1 plus x minus 2 plus x minus 2 squared over 2 factorial So the only difference from your original function is that you're going to substitute in x minus 2 because your a is equal to 2, and yeah. Okay, so to find the interval of convergence for the function, you're going to have to use your ratio test, which x of n is going to equal x to the n over n factorial, which is your general term, and then your a sub n plus 1 is going to equal x to the n plus 1 over n plus 1 factorial. So you're going to have to take the limit as n approaches infinity of the absolute value of a sub n plus 1, which is going to be x to the n plus 1 over n plus 1 factorial, and then you're going to be dividing by your a sub n, so you're just going to multiply by the reciprocal, which is n factorial over x to the n. So these two terms are going to equal x, and these two terms are just going to equal 1 over n factorial. So you take your limit as n approaches infinity of the absolute value of x, because you're solving for x and you know that your n is going to be going towards infinity. So as your 1 over n factorial gets larger, it's going to equal 0, which makes your whole limit 0, which means that your interval of convergence is going to be negative infinity to infinity. Okay, so this is going to be, it's a little different for your binomial series. So to find the Maclaurin series for f of x, which equals 1 plus x raised to the p, with p as a constant, but not necessarily a common integer. Here is how you're going to generate it. Okay, f of x equals what we just said before, 1 plus x raised to the p, and then we're just going to be taking a derivative like normal.
I wish we looked this on the screen, but don't tell anybody else.
Just taking a derivative. You're going to find your f of 0, your f prime of 0, your f double prime of 0, and your f triple prime of 0. So your f of 0 is always going to equal 1, and your f prime of 0 is going to equal p, and your f double prime of 0 is going to equal p times p minus 1, and your f triple prime of 0 is going to equal p times p minus 1 times p minus 2. And altogether, the binomial series looks like this. Px plus p times p minus 1 x squared plus p times p minus 1 times p minus 2 x since they're 1 and 3 factorial. And that would just be to the third degree.
Okay. For our first example, we're going to find the nth-term polynomial for f of x equals e to the 4x, and we're going to find that to the fourth term. So, e to the 4x. So that is our original function, and now we're going to take up to the fourth derivative. since it did not give us a number to center it around, we're just going to center it around 0. So plug these all in for 0. So here you get 1, plug 0, 4, 16, 64, and wait, yeah, 64 and 256. And then you can formulate your Taylor polynomial, getting e to the 4x is approximately your fourth term equals 1 plus 4x plus 16 over x squared, or 16x squared over 2 factorial plus 64 x cubed over 3 factorial plus 256 x to the fourth over 4 factorial, and then you can simplify that. For a second example, the function f has derivatives of all orders for all real numbers x. Assume f of 2 equals -3, f prime of 2 equals 5, f double prime of 2 equals 3, and f triple prime of 2 equals -8. With this information, we're going to write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 1.5. So to do this, we see the equation they give us. They give us our original function and all of our derivatives. So from that, you can take p of 3x, because they give us up to the third derivative, and equal -3, which was our solution to the original function. And then our first derivative is 5. And you do that times x minus 2, since our function is centered around x equals 2. And then plus what they gave us here, there's 3 x minus 2 squared over 2 factorial. And then minus 8, what they give us, so 3 factorial times x minus 2. And that would be your third degree. But then we're still trying to find 1.5. So you go down here, you plug in 1.5 equals, but since it's -2, what you would have to actually like plug in, you would say that it was p of 1.5, but you would have to subtract it, so you would take your what you're doing, which is your x, so x equals 1.5, and you would have to do -2. So what you're really plugging in is -0.5. So we go here, and for x, we plug in 0.5. So with that, you would get approximately -4.958. For our last example, we're going to be finding the Taylor polynomial from f of x equals 2 over x. We're going to be doing this centered at 1 and do that for 3 terms. So that means that we need the original function, which you can rewrite that as 2x to the -1, and take up to 3 derivatives of that, since we are finding the third term. So we have what's given to us, f of x equals, which another way to write 2 over x, would be 2x to the -1 power. And then we can take 3 derivatives of that, so f prime of x equals -2x to the -2, f double prime of x equals 4x to the -3, and f triple prime of x equals negative 12x to the negative 4. Now we're going to plug in 1 for all of those since the function is centered around 1 instead of 0. 1, you get 2, plug in f prime of 1, you get negative 2, plug in f double prime of 1, you get 4, and f triple prime of 1, you get negative 12. And so, now you can formulate your final function. So you would get 2 over x equals p of 3 of x, since we're finding our third term, equals 2 minus 2 times x minus 1 plus 4 times x minus 1 squared over 2 prime, and then minus 12 times x minus 1 cubed over 3 prime. And then you can simplify that to get to your final function. Alright, now that we've reached the end of the lesson, these are some 2 homework problems to use.
A valuable lesson on the history of calculus. What is calculus? Calculus is the study of continuous change. Calculus teaches you to solve problems that you have already learned in a different way. It is a form of mathematics that expands and builds on prior knowledge. Sir Isaac Newton. He was born on January 4th, 1643, and died March 31st, 1727. Newton did not have any children or a wife. His mother's name was Hannah Oskow, and his father's name was Isaac Newton Sr. He attended the King's School from 1655 through 1660 and Trinity College from 1661 to 1665 and 1667 to 1668. He discovered calculus, developed 3 laws of motion, advanced early modern chemistry, devised a law of universal gravitation, invented the reflecting telescope, and proposed a new theory about light and color.
René Descartes. Birth date March 31st, 1596. Death date February 11th, 1650. His parents were Joachim Descartes and Jeanne Brocard. Descartes' mother died when he was 1 year old. So his father remarried and René's, leaving him in La Haye to be raised by his maternal grandmother and then by his great uncle in Châtellerault. I don't even know. While he was residing in Amsterdam, he had relations with a servant girl, Helena Hans van der Storm. He had a child with her, his only daughter, Francine Descartes, born in 1635 in Devontier. She was baptized Protestant and died of scarlet fever at age 5. Descartes attended the Jesuit college at La Fleche in 1606, where he was trained in military engineering, the judiciary, and government administration. In 1614, he went to the University of Poitiers, where he earned a law degree in 1616. He also attended Leiden and Franeker universities to further his education and research opportunities. He was best known for discovering an important connection between algebra and geometry and into analytic geometry. Our cool math fact. A circle has the largest area of all shapes with the same perimeter and the shortest perimeter of all shapes with the same area. Our quote was the same as our poster quote, "Calculus is the most powerful weapon of thought yet devised by the wit of man," by Wallace B. Smith. And then these are our citations.